Hello brainy folks, it's me again, DanielAryee. Welcome back to my tutorials in neuroscience, a very exciting field that seeks to study the brain, the nervous system, etc. in an effort to largely understand neurons and the communication between these neurons, including other important related, complementary, and supporting cells. Yes, today I will take you through a series of important calculations regarding the bits and pieces of a very important biophysical equation in neuroscience known as the Hodgkin-Huxley model, a powerful workhorse in neuroscience. Yes, specifically, you will learn how to calculate ionic conductances of sodium-potassium leak channels, net ionic current flow, and even possibly calculate the excess current required to reach the threshold potential if the net current flow to the neuron in question per the calculation is not sufficient to depolarize that neuron. Yes, by the time you are through with this exciting tutorial, you will understand the specific contribution of ionic elements like sodium, potassium, etc. in starting action potential, known in neuroscience as neural signaling, which involves but not limited to depolarization. In other words, you will get to learn about one of the most important focal objective of the Hodgkin-Huxley model, as it seeks to describe the ionic mechanisms underlying the initiation and propagation of action potentials, etc. in neurons. Great! Alright, let's get the ball rolling with the following scenario. Determination of action potential in neuroscience by DanielAryee, December 29, 2024. Question: consider this scenario where a neuroscientist wants to determine the communication between neurons as a function of net ionic current density and the conditional excess amount of external current needed for action potential in the context of neural signaling, now based on the data below. With given threshold potential of negative 55 MV, membrane potential of negative 65 MV, and membrane capacitance of 1 microfarad per square centimeter. Including the equilibrium potentials, values of sodium, potassium, and the leak channels as 50, minus 77, and minus 54.4 MVS respectively. In addition, data about the conductances and associated gating variables probabilities are also given as follows. GNA max equals 120 millisiemens per square centimeter, probabilities M equals 0.05, H equals 0.6. GK max 36 millisiemens per square centimeter, probability N equals 0.32. GL equals 0.3 millisiemens per square centimeter. Calculate the net ionic current in addition to the excess amount of current needed to reach the threshold potential. Good. So solution step 1, state the Hodgkin-Huxley model and identify key variables. Thus, Cm multiplied by dVm/dt equals total membrane current minus net ionic current. This can be rewritten as is equals Cm multiplied by dVm/dt plus Ic. Membrane capacitance, Cm. Resting membrane potential, Vm. Threshold potential, Tp. Total membrane current, is. Ions and leak channels. Sodium, Na. Potassium, K. Leak channel, L. Equilibrium potentials. Conductances. Max sodium conductance, GNA. Max potassium conductance, GK. Leak conductance, sad phase, GL. Sodium conductance gating probabilities, M, H. Potassium conductance gating probability, N. Great, next. So solution step 2, write down given values in the question. Cm equals 1 microfarad per square centimeter. Vm equals negative 65 millivolts. Tp equals negative 55 MV. Equilibrium potentials. Sodium, ENA equals 50 MV. Potassium, EK equals negative 77 MV. Leak channel, EL equals negative 54.4 MV. Conductances. GNA max equals 120 millisiemens per square centimeter, probabilities M equals 0.05, H equals 0.6. GK max equals 36 millisiemens per square centimeter, probability N equals 0.32. GL max equals 0.3 per square centimeter. Great, so now we can proceed to the next solution step by calculating the specific ionic current densities, after which we shall calculate the net ionic current density, or what is also known as net flow current. Alright. So solution step 3 calculates sodium ionic current, but here is the catch. Sodium conductance are affected by gating probabilities because it depends on those activation and inactivation gates, so we need to first recalculate that before calculating the current. Thus, Gn a conductance can be written as Gn a max multiplied by m raised to the cubic power times h, or simply Gn a equals Gn a max times m cubed times h. Hence, after substitution where Gn a max equals 120, m equals 0.05, h equals 0.6. Gn a becomes 120 multiplied by 0.05 raised to the power 3 multiplied by 0.6. Therefore, after computation, Gn a equals 0.09 millisiemens per square centimeter. Great. At this point, having calculated the conductance, we can now calculate the current as sodium current equals conductance multiplied by the difference between the membrane potential and its equilibrium potential, or simply rewritten as Ina equals Gn a multiplied by Vm minus Ena. Okay, here we need to substitute the values where Gn a equals 0.09, Vm equals minus 65 and En equals 50 into the above equation. This gives the sodium current as I Na equals 0.09 times minus 65 minus 50, implying that Ina equals 0.09 times minus 15. Therefore, the sodium ion current density after the mathematical manipulation equals 10.35 microamps per square centimeter. Next, for same reason as above, let's calculate the potassium ionic current. Thus, Gk conductance can be written as Gk max multiplied by n raised to the 4th power, or hence after substitution where Gk max equals 36, n equals 0.32, implies that Gk equals 36 times 0.32 raised to the power 4. Therefore, after computation, Gk equals 1.18 millisiemens per square centimeter. Great. At this point, having calculated the conductance, we can now calculate the potassium current to be equals to conductance multiplied by the difference between the membrane potential and its equilibrium potential, or rewritten as Ik equals Gk times Vm minus Ek. Okay, here we to substitute the values where Gk equals 1.18, Vm equals negative 65 and Ek equals negative 77 into the above equation. This implies that the potassium current Ik equals 1.18 multiplied by negative 65 minus negative 77, implies that Ik is equal to 1.18 times 12. Therefore, the potassium ionic current density after further mathematical manipulation equals 14.16 microamps per square centimeter. Alright, let's move on to leak current. Here it must be noted that we do not need to recalculate the conductance because its conductance has an implied probability of 1. Yes, the leak current can relatively be quickly calculated using the formula below since its conductance is not affected by the probabilities of gating variables. Thus, leak current equals conductance multiplied by the difference between the membrane potential and its equilibrium potential, or can simply be rewritten as IL equals GL multiplied by Vm minus EL. Okay, here we need to substitute the values where GL equals 0.3, Vm minus 65 and EI equals minus 54.4 into the above equation. This implies that the leak current IL equals 0.3 multiplied by negative 65 minus negative 54.4. Hence IL equals 0.3 multiplied by negative 10.6. Therefore, the leak current density after further mathematical manipulation equals negative 3.18 microamps per square centimeter of an area in the neuron's membrane. Great, we have come very far, and at this point we can now proceed to the next solution step, to calculate the net ionic current. So solution step 4, net flow of current is equivalent to the sum of all the specific ionic current densities in addition to the leak channel's current density. So, net ionic current equals sodium current density plus potassium current density plus leak channel current density, or can be simply written as IC equals INA plus IK plus IL. Therefore, after substitution where INA equals negative 10.35, IK equals 14.16, IL equals negative 3.8. implies that the net ionic current will be equals to minus 10.35 plus 14.16 plus negative 3.18. Therefore, after mathematical manipulation, the net ionic current equals 0.63 microamps per square centimeter of an area in the neuron's membrane. Great! So here we are. It's time to proceed to the next solution step to determine depolarization. However, we can do that by calculating the rate of change of the neuron's membrane potential. Yes, that is how to find out if the net ionic current in solution step 4 can depolarize the neuron. Good. So solution step 5, determination of depolarization can be accomplished using the formula below. Rate of change in the neuron's membrane potential with respect to time equals the net ionic current divided by the membrane's capacitance. This can simply be rewritten as ddm/dt equals IC divided by Cm. At this point, we need to substitute the values of IC equals 0.63, Cm equals 1 into the equation above. Rate of change in the neuron's membrane potential with respect to time equals 0.63/1. This can also simply be written as ddm/dt equals 0.63 divided by 1. Therefore, by further mathematical manipulation, ddm/dt equals 0.63 microamps per square centimeter. But here, get this kicker, yes, for a quick interpretation of the results above. I can confidently say that the rate of change in the neuron's membrane potential with respect to time is 0.63 microamps per square centimeter of an area in the neuron's membrane. Yes, this value can cause depolarization, but just slow depolarization because the value, though positive, is scanty compared to the tracehold potential. Alright, great. To this end, let's proceed to the final solution step. But before then, remember, we just realized that the calculated ionic current or net flow current density, thus the current acting or received per square centimeter unit area of the neuron's membrane, though positive, it is still not enough, and will only cause slow depolarization. Hence, for greater results leading to effective action potential, we would have to calculate for the excess or additional amount of external current needed. Okay, let's go. Yes, let's get the ball rolling. So solution step 6. Now to calculate excess current needed. First of all, as a first step in the process of doing that, let's determine the required change in voltage given by the difference in the threshold potential and the membrane's potential. This could also simply be rewritten as delta V equals to Tp minus Vm. Therefore, after substituting Tp equals negative 55 and Vm equals negative 65, induces delta V to be equals to negative 55 minus negative 65. Hence, after further mathematical manipulation of the above, delta V equals 10 millivolts. In other words, the difference of voltage between the threshold potential and the membrane potential is 10 millivolts. Now it's time to calculate the change in current, which is the next or second step in the process towards determining the excess amount of current required to reach the threshold potential by using the formula below. Change in current equals membrane's capacitance multiplied by change in voltage. This can simply be rewritten as delta I equals Cm multiplied by delta V. Therefore, after substitution of Cm equals 1, delta V equals 10 into the equation above, delta I will be equals to 1 multiplied by 10. By further mathematical manipulation, delta I equals 10 microamps per square centimeter. Yes, this is the current required to reach the tracehold potential. Therefore, using this result as our base value, we can finally calculate the excess or additional current needed to reach the required threshold potential, which we just calculated above. Hence, excess current required will be equals to the difference between delta I, which is 10 microamps per square centimeter, and the calculated ionic current density, which 0.63 microamps per square centimeter. This can simply be rewritten as excess current required equals delta I minus IC, which after substitution implies that excess current required equals 10 minus 0.63. Therefore, after manipulation, the excess current required equals 9.37 microamps per square centimeter. So now, in conclusion, I can confidently state that the additional external current density needed is 9.37 microamp per unit area of a squared centimeter of the neuron's membrane. Yes, it corresponds to the required voltage necessary to bring the membrane potential to the tracehold. Any current more than that would exceed the threshold of 10 microamps per square centimeter and hence will induce the neuron to attain full depolarization and possibly have other phases of action potential triggered. So elegant, isn't it? Ha, ha, ha. But here is the thing. Again, get this kicker. Thus, in other words, the neuron requires an additional 9.37 microamps per square centimeter to reach its threshold potential, and any current in excess of 10 microamps per square centimeter, or say any single current addition to that, will lead to full depolarization comprising different phases of action potentials, including depolarization, repolarization, or even hyperpolarization. Wow! So elegant. Ha! Ha! Yes, is your man DanielAryee here, giving you the best of tutorials on the application of the Hodgkin-Huxley model to the excitability of neurons encapsulated into the action potential processes in any human brain cells, yes, on my YouTube channel at DTechnology4. However, before you exit, I would love to increase your retention on certain key facts and nuances. So here are a few things stipulated in the supplementary explanations below for you to learn and retain into memory. Great! Supplementary explanations. 1. It is important to note that the realized net ionic current in the solutions above indicates a dominance of the outward potassium current over the sodium inward current, but that scanty current can still generate slow depolarization. In other words, the net flow of current is 0.63 microamps per square centimeter. And this, by interpretation and implication, can depolarize the neuron towards the effort in starting an action potential, though slowly. This is because the net flow of current is positive, though scanty, and hence has the tendency of causing the neuron to be less negatively charged or reduce the negativity of the neuron membrane potential, a condition necessary to trigger depolarization of the neuron from its restful or ground state into excitability towards initiating an action potential or neural signaling. Meanwhile, the details and other nuances of the neuronal mechanics will be covered in separate tutorials. 2. Stemming from the preceding fact, it will be very useful to recognize that additional polarization is necessary for effective action potentials. In other words, that additional current, when combined with the already determined ionic current density from the previous solution steps, will be enough to increase the activity level of the controlling mechanisms known as gates on specific protein structures called channels to allow the reception or the flow and passage of ionic current into the targeted neurons with just the right amount of current, either equivalent for the threshold or in excess of it, in order to initiate effective action potential, or better still, start the process of what is known as neural signaling in neuroscience. Yes, these gating variables are dependent on membrane potential or voltage, which explains why they are affected by additional currents. However, it is equally essential to note that depolarization is just the first phase of action potential, and it represents any change in the membrane potential that makes it less negative than at resting state of negative 65 MV. Therefore, 0.63 microamps square centimeter indicates that the neuron may need additional external current of exactly 9.37 microamps per square centimeter, or in excess of 9.37 microamps square centimeter, to reach the threshold current and eventually full depolarization, since any current greater than 10 microamps per square centimeter will start action potential. Besides, it's very important to know that the rate of change of capacitance is the difference between total membrane current and net ionic current or inward current. Total membrane current includes, in addition to ionic current, other capacitive elements. Indeed, the whole Hodgkin-Huxley model hinges on the mathematical relationship above. 3. Finally, let me throw some more light or illumination on the gating variables. Thus, they are probabilistic variables that affect sodium and potassium ions conductance, yes, indicating the probability that specific ionic gating channels are opened. Thus, essentially as gating variables, they contribute and serve as part of controlling mechanisms that determines how the protein structures called channels allows the passage of current flow through the neuron's membrane, and by extension affects conductibility. Because this truth, it is clear that the gates depends on the membrane potential. For instance, the M indicate the probability that the sodium activation gate is being opened, whilst the H indicates the probability that the sodium inactivation gate is being opened, whereas N indicates that the probability of the potassium activation gate being opened. However, at this point please bear in mind that the leak channel conductance is not affected by these gating variables and that is reflective of the inherent characteristics of the channel, which predisposes it to constant and continuous permeability. Thus, in other words, the channel allows flow of current with an implied probability of 1, or alternatively, we can say it allows the continual flow of current with a constant probability, but the former description makes a perfect mathematical sense. Then the later, yes, in other words, it is more mathematically precise. Besides, I would want you to also learn about the fact that these gating variables are both time and voltage dependent values. They are governed by differential equations. Precisely, it is dependent on steady states equations and can be derived and calculated from experimental data by recording the behavioral manifestation of ionic currents. Meanwhile, I will teach you on those complex details in another episode in the series of my exciting tutorials. Yes, in the next video, I will take you through details of full depolarization, exact depolarization, nuances and misconception about negativity or positivity when it comes to the concept of depolarization, which leads to action potential. Yes, the tutorials even includes complex computational modeling of neurons involving calculation of steady-state values. Once again, I am DanielAryee. Thanks for watching, and please don't forget to like, share and subscribe to my channel at DTechnology4. See you in my next video. As usual, remember to keep expanding the frontiers of your knowledge. Yes, never stop learning. Take care, bye.